In your previous chemistry course, you may have been tasked to memorize strong acids and bases, like the ones on the screen. However, more species exist as weak acids and bases than strong acids and bases. I want to paint acids and bases in a different picture. You may consider acidity and basicity as a black and white picture. A species is either one, and can only exist as either one. However, this perspective is mostly untrue. Except for your strong acids and bases, most species, and all organic molecules, exist on a spectrum of acidity and basicity. A species may act as a base when mixed with one solvent. However, it may act as an acid when mixed with a different solvent. This is useful to understand when given reactions to solve. In the case of these two molecules, how do you know which one will act as the acid and which one will act as the base? There is a very useful mnemonic to remember the order of examination to compare two molecules in terms of acidity, ARIO. We'll be adding the letter C to this mnemonic later, but for now let's focus on the mnemonic we have on hand. A stands for atom. When comparing acidity, the first thing you should look at is the atom that the hydrogen is attached to. Acidity increases right and down on the periodic table. As you go right, elements get more electronegative, which means they will be more willing to capture and hold an extra lone pair if the proton is lost. As we go down the periodic table, elements get larger and larger, meaning that some extra electrons won't affect the stability of the element much. For example, when comparing a hydrogen attached to a carbon versus a hydrogen attached to an oxygen, the latter will be more acidic. R stands for resonance. When a species loses a proton and becomes negatively charged, the resonance around a negatively charged atom will help distribute the negative charge across the molecule. Therefore, it'll be more willing to give away that proton to become negatively charged. The best example for this is a carboxylic acid versus an alcohol. In both species, the proton is attached to oxygen, so we must move on to compare resonance. Carboxylic acids inherently have a large amount of resonance, as the negative charge can delocalize among the two oxygens. In alcohols, however, resonance is non-existent. Therefore, carboxylic acids are more acidic than alcohols. I stands for induction, or inductive effect. The inductive effect is characterized by a strongly electronegative group existing nearby the acidic proton. For example, if we compare these two carboxylic acids, we'd see that they are almost the same, except the one on the right has a fluorine 1 carbon away from the acidic proton. When the two species lose their protons, the negative charge will be distributed due to resonance, but the fluorine will help distribute a partially negative charge further across the molecule. This makes the molecule on the right more acidic. However, it's important to point out that this rule exists for electron withdrawing groups only. Halogens are a great example of electron withdrawing groups. Carbons or alkyl chains are electron donating. If we were to replace the fluorine from the previous example with a methyl group, the acidity would decrease below the molecule on the left. The last letter, O, stands for orbital. As hybridization value increases, acidity decreases. For example, compare these three carbon species. All of them show a hydrogen attached to a carbon, show no resonance, and have no inductive effect. However, if a negative charge were to exist, the sp hybridized carbon would be able to handle it much better than the sp2 hybridized and sp3 hybridized carbon. The sp2 hybridized carbon would be able to handle the charge much better than the sp3 hybridized carbon. sp3 hybridized carbons are actually the least acidic species you can encounter. There are two major exceptions to this mnemonic that you should commit to memory. First, if we were to compare a nitrogen or an amine to a carbon, we would expect that the amine would be more acidic than all of the carbon species. However, amines are not stronger than sp hybridized carbons. They are, however, still stronger than sp2 and sp3 hybridized carbons. The second exception is a great example to introduce a letter in the mnemonic that I purposely left out. C, or charge, can turn your rules upside down. For example, a nitrogen that has a positive formal charge, like the ammonium ion, is going to be stronger than most alcohols, even though the hydrogen is attached to an oxygen. However, the positively charged nitrogen will still be weaker than carboxylic acids. When we compare species, charge can throw all of your other rules in the garbage. For instance, a positively charged oxygen atom, like the hydronium ion, will be more acidic than most carboxylic acids. Therefore, Sometimes we say the mnemonic as CARIO, not ARIO. In some courses, your professor provides you with a pKa table for reference. However, this table will not specify small differences in molecules, and you will certainly not understand why substances are stronger or weaker than others just by using the chart. In the next video, we'll talk about the leveling effect and how to determine if an acid-base reaction will go to completion.